Guys, wait for a while. Okay, I think I can start now because most of you are here. 36. All right, let me start now. Now I'm going to share the screen. Hopefully everybody can see the screen. All right, now everybody can see the screen. Please type in the thing. Please type in the if everybody can see the screen. Okay. Good. All right, so most of you can see the screen. Okay, I understand. Let us start before wasting any time. Okay, we are going to learn chapter 5. Okay, I understand. Okay, thank you. Okay, in this chapter 5, I'm going to teach you two things. Okay, hopefully I can finish by 1 and 15 minutes. Okay, first thing I'm going to teach you is network representation. What is network representation? I'm going to go quick, very quick. Okay, you no need to copy anything. Just take down some notes because I'm going to share all the notes whichever I write here in the group. Okay, let us start. Example 1. If you read this example, first example, if you read the first example, you can see that no. Okay, I cannot wait anymore because time is running out. Okay, if you see this, Foster Generators operates plants in Cleveland, Bedford, and York. Okay, there's 3 plants. Okay, 3 factories which produce generators. Production capacity over the next 3-month planning period for one particular. Okay, blah blah blah. Now, basically, example 1 tells you that. Example 1 tells you that. Mute your mic. Mute your mic. Yep, thank you. Mute your mic. Example 1 tells you that there is. So I'm doing the network representation. It tells you that there are 3 plants and each plant produce generators. How much they produce? The first plant, which is in Cleveland, it produced 5,000. Bedford, it produced 6,000. And York, it produced 2,500. Okay. Now, these 3 factories, they produce and they deliver to the customer. So how many customers are there? 1, 2, 3, 4. 4 customers. Where are the 4 customers? These are the 4 customers. Boston, Chicago, St. Louis, and Lexington. So these are the customers. These are the suppliers. So each customer, they do have their own demand. If you read this, they do have their own demand. 6,000, 4,000, 2,000, and 1,500 each demand. So how this network representation goes? is just you have to join each circle here with this each circle. If you notice here, I leave some space here. Okay, that is for the later use. Now, how the network looks like is just like matching. Okay, matching the thing. So Cleveland will send some unit of product to Bedford. It also can send to Chicago. It also can send to St. Louis. It also can send to Lexington. Now, each time it sends one unit to Bedford, it costs Cleveland how much? You can see the cost here. Cleveland to Boston, how much is the money? $3. Put 3 here. So this 3 ringgit cost is 1 unit for 1 unit. So depends on the unit. Later on, you're going to multiply with the unit. Those who cannot join later on, I'll open a class 3. Okay, don't worry. Okay, so from here, Cleveland to Bedford, it will cost you 3 ringgit or $3 per unit. Cleveland to Chicago, it is $2. Cleveland to St. Louis, it is 7. Cleveland to Lexington, it is 6. Okay, so same goes. This is how you have to draw the network representation. Okay, this is how you have to draw. Same goes to next one. Bedford can send to all 4 customers. York can send to all 4 customers. It's just you need to write the cost. This would be 7, 5, 2, 3. York is 2, 5, 4, 5. Okay, hope you guys understand. It's very easy, very simple. Today I'm going to do a very simple thing, not solving any maths because time duration. Okay, next class next class is the important class. Okay, today just some kind of introduction. This is supply, this is demand, and this is your network representation. Okay, now I'm going to give some okay, this is the thing. Network, when the question asks you to do network representation, you do this, you will get the full mark. Okay, now after network representation, our next aim is linear programming model. Okay, how we going to come out with a linear programming model from the transportation problem. Okay, you guys still remember maths, the linear programming? The first thing is you will write something like this: 2a plus 3b, and then subject to some 3a plus 5b, that's all equal to 7, blah 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 blah, and then a minus equal to this. Okay, this would be your objective function. This is your objective function. These are the constraints. This is what we have done in maths for linear programming. The same thing we're going to do here. Okay, thing is, in maths we find what is the quantity of A, what is the quantity of A and B, so that you get a maximum profit or minimum cost. The same thing we are going to do here. When the question asks you to develop a linear programming for this network representation, first of all, what you have to do, we have to give a notation for each quantity from one supply to destination. Okay, so how are we going to identify quantities? How are we going to give notation for the quantities? Notation, X, Y, Z, A, B, C, Y, any notation. the quantity from Cleveland to Bedford, the quantity from Cleveland to Chicago, Cleveland to St. Louis, Cleveland to Lexington. So this notation must be different. So how are we going to do this? We're going to give some number. 1, 2, 3, 1, 2, 3, 4. Okay. So remember, what we are doing now is transportation problem. In transportation problem, it is very important to know what are the quantities from each supply to customer. So this plant can produce 5,000. Out of 5,000, how much it can give to this Bedford, because they need 6,000. Okay, how much this one can give, how much this one can give, how much this one can give. So before we solve this, okay, before we solve this, we have to come out with some linear programming model. And for that, we need to give notation for the quantity. So how are we going to give the notation? This is the procedure. The notation of quantity from Cleveland to Bedford, I will write like this. X 11. X11 means 1 to 1. Okay, that is the notation. The quantity from Cleveland to Chicago, what would be the notation? 1, 2. And then to Cleveland to St. Louis, 1, 3. And then goes on. Okay, that's how we give the notation of quantity from each supply to a destination. So if I write this, 1, 2, 1, 3, 1, 4. Okay, this is for from Cleveland. From Cleveland, the quantity, the notation of the quantity from Cleveland to Bedford, Chicago, St. Louis, and Lexington are these. These are the 4 things. Okay, 1, 1, 1, 2, 1, 3, 1, 4. These are the quantity. Okay, bilangan. The same thing we can do for Bedford and York. Okay, so each line here is from Cleveland, this one is Bedford, this one from York. These are the quantity, okay, each quantity. But what is our aim? Our aim is, our objective function is actually minimize the cost. Okay, our Z is minimize the cost. So these are the quantity. Now you insert the cost for each of them. The cost of 1 unit from Cleveland to Bedford is 3 ringgit or $3. How much you move, how much you give, what is the quantity? X11. So you times with the cost. 3, 2, 7, 6, 7, 5, 2, 3. Okay. So this would be your objective function. This is your objective function. Now, again, for LP model, linear programming model, we need objective function. Next, what do we want? We want constraint. We want constraint. What are the constraints related to this thing? First constraint, you have to see. Okay, first part of constraint is related to supply. Okay, supply here. Now, again, it related with quantity. Remember, Cleveland, remember in Cleveland, it only can produce 5,000. So whatever quantity goes out from Cleveland must be less or equal to 5,000. All right, that is some idea you need to understand. Each supplier only can give you whatever they have produced here. So Cleveland produced 5,000, Bedford produced 6,000, this one produced 2,500. Each quantity goes out from each supplier must be less or equal to this figure here. So the first part of constraint is like this. What is the quantity goes out from here? 1, 1, 1, 2, 1, 3, 1, 4. All these must be less or equal to 5,000. So 1, 1, 1, 2, 1, 3, 1, 4 must be less or equal to 5,000. And same goes for the other one. 2, 1, 2, 2, 2, 3, 2, 4 less or equal to 6,000. This is the first part of constraint, which is from supplier part. Okay. Now, this part done, supply, this constraint done. Now we move on for the demand, customer. Okay. Each customer, they need, this one, Bedford needs 6,000, Chicago needs 4,000, St. Louis 2,000, Lexington 1,500. When the customer asks some quantity, as a supplier, you need to provide them what they ask. Okay, you need to provide what they want. If they ask for 6,000, you have to make sure 6,000 is there. It cannot be less, it cannot be more. So the next part of constraint is whatever quantity goes inside here, must be equal to 6,000. Whatever quantity goes inside here must be equal to 4,000. This quantity 2,000. That's how you're going to construct the constraint. Okay. What quantity goes inside Bedford? 1, 1, 2, 1, 3, 1. 1, 1, 2, 1, 3, 1. This must be equal to 6,000. It cannot be less, it cannot be more. Supplier can, customer cannot. The next one after Bedford is Chicago, I think. Yes, Chicago. 1, 2, 2, 2, 3, 2. Okay, this is second part of the constraint. So you guys notice that first I develop the objective function. Second, I develop the constraint. In this case, in this transportation problem, I develop from supplier first, and then I go for demand. The final one is non-negativity constraint. You still remember, you always write A, B greater or equal to 0, something like that. Okay. In this case, what you write? Xi greater equal to 0. I is the starting point of the line. You see where the line start from. It start from here, end up here. It start from here, end up here. Start from here, end up here. So each and every line start from 1, 2, 3. So I is 1, 2, 3. Clear? That is I is starting point. Starting point. J is finishing point or ending point. Okay. So you have to see where the line end up. The line end up at 1 again. The line also end up at 2, 3, and 4. All the lines end up in 1, 2, 3, 4. So write the number 1, 2, 3, 4. Okay. This how you construct a linear programming model for transportation problem. Okay. This how you construct network representation for transportation problem. Okay. Let us do number 2 now. Example number 2. Okay. This is the answer I have given here. You can check. It is the same thing. Number 2. If you read this, number 2, again, don't copy all. I just want you to guys sit, relax, and try to understand. Okay. Example 2, network representation. If you read this example, you can see the supplier. We have 3 supplier. Okay, if you went through this, just read as quick as you can. The supplier is 150, 175, 275. That is the quantity, maximum quantity each supplier can supply. This is Kansas, Omaha, and Des Moines. I don't know what is the name actually. That is supplier. How many customers are there? Customers also we do have 3. Chicago, St. Louis, and Cincinnati. How much they need? 200, 100, and 300. And after this, you can draw the line. Each supplier are eligible to send their product to each customer. Okay, like this. And then what to do? Write the cost. Kansas to Chicago, Kansas to St. Louis, Kansas to Cincinnati. You can see four, 5, 12, and then finally you just put 1, 2, 3, 4. Sorry, not 4. 1, 2, 3. Supply, demand. This is network representation. In the final, there is one question. You need to do this kind of things. Okay. So if the question asks, that's it. This is the answer. You will get the full mark. Now after this, what you have to do? Second one. If the question asks. If the question doesn't ask, don't do the second one. Second part is what? LP model. Linear programming model. So how are we going to do this? Of course, because it incur cost. Okay, it is related cost. Therefore, we minimize each cost for each quantity. So first of all, give the notation for each quantity from each supply for each destination. So Kansas to Chicago, the notation for the quantity should be 1, 1. The notation for quantity Kansas to St. Louis 1, 2, and so on 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. 1, 1, 1, 2, 1, 3 plus 2, 2, 2, 3, 3, 2, 3, 3. So these are the quantity as we did in the previous question. After this, what you have to do? Times with corresponding cost. that would be 6, 8, 10, 7, 1, 1, 1, 1, 4, 5, 12. Okay, so this would be your objective function. Of course, you don't need to write this. This is just for your understanding. After this, what to do? Subject 2. We're going to find the constraint. As I told you before, as in the previous example, the constraint must start from the supplier first. Now, what are the constraints? The quantity which comes out from cancers must be less or equal to 150. This one must be less or equal to 175. This one 275. So to help you, you just put 1, 2, 3. This one is must be less 150, 170, 270. Okay. What are the quantities here? What are the quantities comes out from cancers? 1, 1, 1, 2, 1, 3, right here. One, 3. Okay. What are the quantity comes out from Omaha? 2, 1, 2, 2, 2, 3. These are the constraints from the supplier. Now, demand. The demand should be 200, 100, 300. So right here, 200, 100, 300, 100, 300. What are the quantities goes inside here? 1, 1, 2, 1, 3, 1. It must be equal. Okay. Three, 1. Next one is 1, 2. 3, 3. Okay. So these are the constraints. You have done the constraint, supplier and demand. The final one is non-negativity constraint. That would be X, I, J. What is your I? What is your J? Look at the line, where the line start. Each line here start from 1, 2, 3. 1, 2, 3. And each line here, each line end up here and here and here. Okay, berakhir dekat sini end up here. So 1, 2, 3. That's it. That is your network representation. Sorry, that is your LP model. Okay. Now, whatever I teach you in these two examples is transportation model. Transportation model is you have a supplier, you have a demand, the product goes straight to customer. From supplier to demand, straight. Okay, no in between, no middleman. Now the next topic is transshipment, whereby you will have a middleman. If you have a middleman, then how goes the network representation LP model? Okay, the rest is same. Now we are going for transshipment model. Transshipment. Look at example 1. Okay, in this example, if you read, you do have a plant. Okay, you have a supplier. You will have 3 supplier. Okay, you can see here plant 1, plant 2, plant 3. So I write here plan 1, plan 2, plan 3. Supply, okay? These are the 3 plants supply product. But does this product straight away go to the customer? No. The answer is no. This product goes to a warehouse, middleman. Okay? There's a middle thing. Okay? Ada in between certain thing, ada orang tengah, middle. It goes to warehouse. From that warehouse, they distribute all the product to the customer. Okay? So in between here, there is a warehouse. Then only the customer comes. How many customers? If you read this question, you will have 2 warehouse and 4 customers. 1, 2, 3, 4. Warehouse is 2. So you can write here warehouse 1, warehouse 2, customer 1, customer 2, customer 3, customer 4. Okay. Now, after this, what you have to do? You write the supplier capacity. How much they can supply here for the supplier. Plan 1 is 450. Plan 1 is 450. Plan 2 is 600. And this one is 380. The customers, how much they need? 300, 300, 300, and 400. Okay, 300, 300, 400. All right, after this, exactly as same with what we did for transportation, each plan 1 can distribute its product to, okay, to warehouse 1 and warehouse 2. So it goes like this: warehouse 1, warehouse 2. Plan 2 also can distribute, and plan 3 also can distribute. So it goes like this. Now, after this, of course, you need to write the cost. The cost would be 478556. These are the costs. Okay. After writing the first part of the line, the second part would be, remember, the product yet to reach the customer. Okay, it is in the warehouse. So now from the warehouse, they need to reach customers. So from each warehouse, they need to distribute to customers. Okay, something like this. And whenever you distribute from warehouse to customer, there is some cost. You can see here 6484. That one comes here. 6484. Another one is 3677. Okay, these are the costs from warehouse to customer. Okay, now almost done. The final one is put a number, but in transshipment you don't put 1, 2, 3 and start back with 1. You continue 5, 6, 4, 5, 6, 7, 8, 9. Okay, these are the numbers. How are we going to identify? Okay, why you are putting the numbers? Why you're labeling the circle with numbers? For us to give notation for each quantity from plan 1 to W1. Okay, the notation for quantity we will use this label here. Okay, the final one you write here, supply, warehouse, demand. So if the question asks you what is the network representation for this transshipment problem, okay, this is the thing. Remember, the only difference between transportation and transshipment is the middleman, the warehouse. Okay, now we have done the network. let us do LP model, linear programming model. Okay. Of course, minimize. We're going to find the quantity. In transportation, there's only one part of quantity from supplier to demand. For transshipment, you have two portions. Okay, you have two portions. One is this, and another one is this. Two portions. Therefore, we're going to see what is the quantity from plant 1 to warehouse 1. After that, we're going to see from warehouse to customer. So we will deal with plant to warehouse, and then we will deal with warehouse to customer. Okay, clear? Now we're going to give the notation, the quantity distributed from plant 1 to warehouse 1. So how much they're going to give to the warehouse. So what is the notation? It would be 1/4. From P2 to W1, 2/4. P1 to W2, 1/5, something like that. Okay, we finish one circle first. We finish plant 1 first, 1/4 and 1/5. 1/4 plus 1/5. This is plant 1 to warehouse 1. Okay. Plant 2 to warehouse 1 and warehouse 2. Okay. The first one is plant 1 to warehouse 1 and warehouse 2. The second one is plant 2 to warehouse 1 and warehouse 2. Plant 3 to warehouse 1 and 2. All right. After this, write the cost. This is only the first part here. Okay. Now we move on to second part. In second part, we need to know what is the quantity going on. Okay. So from warehouse 1 to warehouse to customer 1, the quantity would be 4/6, and then goes on. Okay, like that. For 6, for 7, for 8, for 9. Okay, this is warehouse 1 to customers. Now we move on to warehouse 2 to customers. Okay, these are the quantity. After this, put the cost. 6, 4, 7, 4. Now this is objective function for the transshipment problem, example 1. Okay. Now we're going to constraint. Okay, constraint. As what we did in the previous one, we focus on the supplier first. Okay, whatever quantity goes out from the each plant must be less or equal to these numbers. So put here less. What are the numbers there? That would be 450. What are the quantity goes out from the circle? That would be 1/4, 1/5. So the first one, 1/5. The second one, 2/4, 2/5. 2, 4, 2, 5. Third one, 3, 4, 3, 5. This is in the perspective of supplier. Okay. Now we move on to customer demand. Well, there is 4 demand. $300, $300, $300, $400. Okay. Now, as I told you, demand cannot be less or more, so it must be equal. So you need to find out what are the quantities goes inside the demand. For customer 1, 46, 56. And then goes, okay, the same goes for customer 2, 3, and 4. This one 47, 57. Okay, these are the constraints for customer. But remember, we are in transshipment problem. Transshipment problem, if transportation we have supply and demand, that's all. But transshipment we have extra thing here, warehouse. Therefore, there's extra constraint for transshipment. Okay, so what is the extra constraint? It is of course related to warehouse. Then how are we going to write it? Okay, listen, this is how we're going to write it. The extra constraint here, whatever goes inside each warehouse must be equal whatever comes outside each warehouse. Let's say you have a warehouse. I give you 100 unit to put in your warehouse. And then I ask you to distribute to each customer. So that 100 unit must go out from the warehouse. You cannot keep. Okay, warehouse is just a pit stop, just a keeping. It's just you keep the things there. Okay, so whatever quantity goes inside warehouse must be equal to whatever quantity comes outside from the warehouse. So for warehouse 1, what is the quantity goes inside? 1, 4, 2, 4, 3, 4. Quantity is 1, 4, 2, 4 plus 3, 4 must be equal to whatever comes outside from the warehouse. So that is 46, 47, 48, 49 must be equal to 46, 47, 48, 49. Okay, whatever goes in must be equal to whatever comes out. Same goes to warehouse 2. Final one is non-negativity constraint. Non-negativity, just put x, I, j greater or equal to 0. Okay, I told you what is I here. I is the label for the starting of the line. Okay, starting point of the line. So let us see from where the line starts. On the first portion, the line starts here, here, and here. So there are 3 points the line start, which is 1, 2, 3, right here. In the second portion, the line start from 4 and 5, right here. Okay, clear? Now, J is the finishing point or the ending point where the line ends up. For the first portion, the line ends up 4, 5. For the second portion, the line ends up at 6, 7, 8, 9. This is the answer for the example 1 LP model. Okay, so be careful in the test or in the final or whatever assessment, whether they're asking for transportation or transshipment. If transshipment, you should be aware that there is a warehouse, middleman. For transportation, there's no middleman, straight away from supplier to customer. Okay, this is example 1. Now we go for example 2. Hopefully you understand clear in example 2. In example 2, if you read this, there will be 2 supplier, 3 warehouse, and 3 plants. Okay. Now, the supplier here, in this question, they call it as a farm. You can see here, farm. Farm 1, farm 2. So I put here F1, F2. Okay. The middleman here, the warehouse here, they call it as grain elevator. So I put it as G1, G2, G3. And the customer here, they call that as mill. Okay, mills. So M1, M2, M3. The farm, the maximum, each farm can produce 300 tons. So you write here 300. 300. What about the customers? The customers can go here, 200, 100, and 300. Okay. Now I'm going to give a label for it. 1, 2, 3, 4, 5, 6, 7, 8. And then I'm going to draw the line. I'm going to write the cost. The cost you can see here, 16, 10, 12. Okay. Next one, 15, 14, 17. 15, 14, 17. That is the cost from supplier to warehouse. Now to warehouse to the customer. The cost given here is this one. 6, 8, 10, 7, 11, 11, 4, 7, 12. Okay. Final one, it would be supply, warehouse, demand. This is network representation for example 2. Hope you get clear picture and idea how to develop this diagram. Next one, automatically what you have to do, model. Okay. Since it is related to cost, we will minimize. Z. Look at this one, F1. Okay, we will settle with the first circle first. The quantity from F1 to G1, 13, 14, and 15. 15. Now we deal with the second circle, 2, 3, 2, 4, 2, 5. Two five. Write the cost. $17. This would be the first part. We do have a second part here. The cost from G1 to M1 363738. And goes on for the other two warehouse. Okay. We have this and we need to put all the costs. So this would be your objective function. Okay. Now you have to write the constraint. The constraints start from the supplier. Okay. Start from the supplier, 300 and 300. You can see here. So whatever quantity goes out from the farm 1 must be less or equal to 300. And this one would be this one is 232425 less than 300. After this, we move on to the customer demand. Demand customer, there are 3 people. That would be 200, 100 and 300. Okay. So what are the quantities goes inside each customer? 36, 46, 56. That's how we have to see. 36, 46, 56, 37, 47, 57, and 38, 48, 58. Okay. This is regarding the demand. Okay. And we still have one more part of constraint, that would be the warehouse. Whatever goes inside must be equal to whatever comes outside. So this is the one. If you see the quantity, that would be, this is warehouse 1. This is warehouse 2. And this is warehouse 3. That's all. The constraint. The final one would be this one, and I equal to j equal to. And I told you I is the starting point. The things start from 1, 2, 3, 4, 5. 3, 4, 5. J is the ending point. 1, 3, 4, 5, 6, 7, 8. Six, 7, 8. Okay, so in this case, this is the answer. So with this, I complete the transportation and transshipment problem, and I teach you how to find network representation and NLP model. You see, whatever we did here, we didn't do any calculation. Okay, we didn't compute, we didn't come across any solution or solve anything, nothing. We just, from the information given, we just identify or develop what is the network representation NLP model. In our next class, we will try to solve certain transportation model. Okay, transportation, not transshipment. We will try to solve transportation model by using northwest corner rule and stepping stone method. Okay, Modi method I didn't cover because not enough time. It's not coming out for your final also. So next class doesn't mean that it will be. Next class doesn't mean that it will be next week. It can be in 2 days or 3 days. Just alert in the group. I will let you know. Okay? When is the next class? This is a very important thing. I need to teach you how to solve this problem by stepping stone method. Okay. With that, another thing, my main idea to having teaching in online is to cover your assessment. So whatever your quiz, assignment, test, final is covering, whatever chapter this assessment covers, I need to teach you first. Okay, I need to finish with that. So I may have as many classes as I want for in online teaching. So I hope I can have your cooperation. Whenever I have online teaching, whatever, you can come and join me. Okay. Those who cannot join this class, I will see how many of them, and if needed, I will open another class, third class, and teach them. With that, that's all for today. Okay. The next class will start with this thing, northwest corner rule and stepping stone method. Okay. After finishing chapter 5, then I will go back to chapter 2. Okay. Chapter 2 needed more time for me. So with that, I hope to see you. I hope to see you in next class. Whenever I put the schedule.